Today we're going to look at how we find the pH of a weak base. The common ones that you'll see are things like ammonia, and then the conjugate bases of a lot of weak acids are good examples. So things like sodium ethanoate, that sort of thing. So what we have to look at first is how a base reacts or dissociates when we put it into water. And a base always makes hydroxide ions when it hydrolyzes. But because this is a weak base, it's an equilibrium, which is quite convenient, because that means that I can write an equilibrium expression for it. So equilibrium expression, remember, has the symbol of K, capital K. This is making hydroxides, so it's called Kb. Makes sense, doesn't it? The little b is for base, just like Ka had A for acid. Kw, W for water, and so on. So I need to be able to write an expression for this. And here I'm going to put the states of matter in black just so you can see the rationale behind this. Remembering that the unit we're doing is aqueous solutions, so we don't worry about liquids or gases or anything like that. We're looking at things that are dissolved in water, so anything that's aqueous. They are the only things we're going to put in our K expression. So on the top we're going to have these two. Whoopsie, why put 4 there? So we get this. Now, those symbols look a bit confusing. So what I'm going to do is next to this, I'm going to do the same thing for ammonia. So I'm going to give you the ammonia equation and the ammonia Kb expression. So when ammonia dissolves in water, it doesn't just dissolve, it dissociates to make the ammonium ion and the hydroxide ions. So my K expression for this one is ammonium times hydroxide, so those two, the concentration of those two, over ammonia. So that might make this one in black make a little bit more sense using actual chemicals. So whenever I see a question where I'm working with weak bases, my first step is to write the dissociation with water equation. My second step is to write the Kb expression. So that's what these are called. The next step is to make some assumptions just like we did with Ka. And I'll show you what I mean by that. If this is a balanced equation, which it is, and I've got X moles per litre of this being made, then I also have X moles per litre of this being made. Which means that that number goes into each of those. So any number times itself is that number squared. Because we're looking at pH, it's the hydroxide that's going to be important. So I can actually rewrite it a different way. Rather than using X, I can do it one of two ways. So the Kb for this one could be the OH ion concentration squared over NH3 squared. Okay? Or,
squared?
sorry, not squared, sorry, just over NH3. Alternatively, this means the same as X squared over ammonia. Okay? So, in case you're a bit confused why I've left the hydroxides in there, it's basically the same thing. Right? There is an assumption there, and it's ignoring the fact that we're going to have some hydroxide ions provided by the dissociation of water. However, because this is a base, that 10 to the negative 7 moles per litre from dissociation of water is going to be pretty meaningless for our final answer. Right, the problem is in a question like this, we wouldn't be given a Kb value. We don't actually get Kb values. What we often get are Ka values or pKa values, which is a bit awkward. That makes things a little bit hard. So how do we work that out? So I'm going to go through an example with you. We're going to try and find the pH of 0.250 moles per litre ammonia. you're given that the pKa of ammonium, so the conjugate acid of ammonia, there it is there, the conjugate acid. The conjugate acid, we're told, and I'm sorry if I got this number incorrect, but that's the one I remember off the top of my head, so we'll go with it, 9.23. Right, well I can see there's nothing to do with Ka anywhere in here. So my first thing is I need to actually find out what the Kb is. Step 1, I've done my equation. Step 2, I've done my expression, noting that it's Kb, not Ka. Step 3, I actually need to find Ka, because there is a relationship between Ka and Kb. And that relationship is this. Kw, which is 10 to the negative 14, we might remember that when we're doing our hydroxide and hydronium ion things, is equal to Ka times Kb as well. Right, now I could spend some time going through the proof for that, but I'm not going to in this case. So it means if I have an equation which has this in it, and I know this value here, and I can calculate this value here from my pKa, then I can actually find this value here to go into our equation. So what does that look like? Well, it means first of all we're going to turn that pKa into a Ka. Alright? So that's actually quite easy to do. If pKa is this, then Ka equals 10 to the power of negative 9.23. I'm going to leave it as that. It's not good maths, but I'm going to leave it like that because it makes my life really easy. If I rearrange this equation here, then I can actually find Kb. Kb equals Kw over Ka, which is 10 to the power of negative 14 over 10 to the power of negative 9.23. Now my maths is good enough to remember what I do when I divide exponents. It's the same as subtracting them. So this becomes 10 to the power of negative 4.77. Negative 14 minus negative 9.23 is negative 4.77. A lot of you got calculators there, so just double check my maths, make sure I haven't made a mistake. Yep, so it'll be 10 to the negative 4.77, so that's good. So closer to 0, that's correct. Okay, so I now have my Kb. Kb equals that. That means I can plug that number into here. Okay, so my next step is to start substituting some numbers in. So bear with me while I use some colours here because it might make it easier to follow later. I've got this one here, 10 to the negative 4.77, so I'll do that in green. That's my Kb. Equals my OH minus ion squared, as per up here, over, in the question it said we have got 0.250 moles per litre of ammonia. Because it's a weak base, we assume it hardly dissociates at all. So we keep that number in there. So this will be 0.250 moles per litre. Now, there's only really one unknown there, so I can solve for hydroxides, and this is where I need you to use your calculators, please. This becomes that the hydroxide ion concentration equals the square root of 0.250 times 10 to the negative 4.77. I'm hoping we get something like 2.06 times 10 to the negative 3. Yeah. Awesome. Okay, so we end up with a hydroxide ion concentration of 2.06 times 10 to the negative 3. Don't forget your units here. It's a concentration, so it's in moles per litre. Right. And then I go back to how I worked out the concentration of a strong base, basically. And that is the relationship with Kw, where it also equals, let's see, put those back to front. The concentration of hydronium times the concentration of hydroxides. So I can use Kw again to work out my hydronium ion concentration. So that's our last step before we find out our pH. If I know this value here is for hydroxides, then my hydronium ion concentration, which is needed for pH, must be 10 to the negative 14 divided by that number there. So, given this, (10 to the negative 14 divided by our answer, and we get 4.85 times 10 to the negative 12. Again, don't forget units. This is a concentration, so moles per litre. And then my last step, my very last step, is to work out the pH. pH is the negative log hydronium. So I'll do that function to this. And we get 11.3. So as you can see, there's a lot more to this. We still start the same way. We write the dissociation equation. We write the dissociation, the equilibrium expression. But you have to be aware that it's a base. Right? Then, after you've got that, we start plugging in the numbers, having worked out our Kb value from the Ka.
With the rounding, because with a weak acid, we can only round to a certain amount of significant figures depending upon the Ka. Is it the same with the base?
Normally with your bases, they're going to be around about that 10 mark, so I'd just say go one decimal place. Okay, it would be quite safe. Look at the data you're given. We were given 3 significant figures here, 3 significant figures here. I think it's fair enough to assume that we're going to be right. With your bases, I think you'd sort of have to get your pKa's up above 11 or 12 before it would reduce its, before it makes your assumption here imprecise to 3 significant figures. So for the ones you're going to get this year, 3 SF is probably good, which is 1 decimal place usually. Okay, yep.
Could we get this question for acids, like when they give us Kb instead of Ka?
Highly, I haven't seen it. I don't see why not. But usually the values you get in data books and so on is pKa.
Okay.
pKa is a really useful number to work out whether something is, how strong an acid something is. So because this is 9.23, it means that ammonium is a really, really, really weak acid. Okay. The thing that I used to get into the trap with this one is I used to see the pKa and write the Ka expression for ammonium. That gets really confusing. So, as I say, step 1, do the base being dissociated or hydrolyzed. 2, do the base equilibrium expression. Then calculate what Kb would have been given the Ka. Then substitute in and solve. Then it's got that extra step. From the hydroxide ion concentration, calculate hydronium, and then from hydronium, calculate pH.